Hello and welcome, class. We are continuing our march through Chapter 2 in this technical lecture series where we are currently dissecting the atom. So in part 1 of this lecture, because you can see here, we are now starting part 2. In part 1 of this lecture, we introduced John Dalton's atomic theory and then started dissecting that, really the first principle, which stated that atoms are indivisible, disproving that by introducing the existence of the electron, the proton, and the neutron. All right, so we also talked about how the electron, proton, and neutron roughly had been discovered, right? I'm not going through a lot of the specific details, the dates, but I am introducing the scientists who made these discoveries and kind of giving more of that historical context for what had been discovered. All right, so where we are picking up then is back with John Dalton's atomic theory. John Dalton's atomic theory had been based off of the Greek philosopher Democritus's idea of the atomos, the fact that, as we have now discovered, that matter is comprised of indivisible, or quote-unquote not indivisible, definite units known as the atom. We also know now that there are 118 different types of elements, types of atoms known as elements. And in our first part, again, part 1 of this lecture, we completely demolished the first premise of John Dalton's atomic theory, that everything is comprised of indestructible atoms, which we discussed as being incorrect because the atom is destructible. It is made of electrons, protons, and neutrons. All right, so if you want that discussion, please go check out part 1 if you have not already. Where we are picking up in part 2 is the second premise of John Dalton's atomic theory, the notion that all atoms of a given element are identical. This is also, by our current understanding, incorrect. And the reason why is because there exist different isotopes and ions of atoms. So you actually have some slight variability between the different atoms, all depending on exactly how many neutrons or how many protons or how many electrons a certain atom has. All right, so since we're not going to be explicitly returning to John Dalton's atomic theory, here is the point where I can say that, yes, John Dalton was 1 for 3. The third premise of John Dalton's atomic theory, the statement that all atoms combine in whole numbered ratios, is still true today. There is no, well, I want to say very decisively, there is no such thing as half of an atom. And the reason why is it really comes down to how we define what an atom is, and that's going to be what we are talking about right now. So the reason why atoms do combine in whole numbered ratios, why, for instance, and this is the past or the previous example I gave as well in part 1, that we have 2 hydrogens and 1 oxygen inside of a water molecule is because you can't have half of an oxygen, you can't have half of a hydrogen. And this is true of all elements. So how do we define an element, and why is it you can't have half of an element or anything like that? Well, the reason why is because an element is defined by the number of protons it has. So if you take one element, like oxygen, and cut it in half, you're actually cutting it in half and creating 2 different atoms. And this isn't arbitrary. The reason why we define an element based off of the number of protons is that we find its behavior, its properties align based on number of protons you have. So if you're looking at a lithium atom has 3 protons. So the number of protons inside of an element is actually equal to the atomic number that is displayed on the periodic table. So we can use this as a way to, as a one-to-one correlation, as a way to figure out how many protons a certain element has. So if we took this element with 3 protons, just a random sampling, let's say of 100 atoms that all had 3 protons, they all would behave very similarly. To the point where you wouldn't be able to tell the difference between an atom that had a different number of neutrons, let's say. The behaviors vary slightly with numbers of neutrons, but they don't vary enough for us to call the element something new. However, if we were to take, let's say, this lithium atom and cut it in half, and we're just going to like ignore neutrons and electrons for this, we're just straight up just looking at protons. Let's say we cut the lithium in half into something that has 2 protons and something that has 1 protons. Well, the thing that has 2 protons is going to start behaving like the element helium, and the thing with 1 proton is going to start behaving like the element hydrogen. And if it no longer looks like a duck, if it no longer looks like a lithium, if it no longer quacks like a lithium, it's no longer lithium, it's something else. And so we can't take an element, break it in half, and still call it the element that we had started with. So the element is going to be defined by the number of protons, and this is, again, based off of consistent experimental observations on the behaviors of atoms in conjunction with how many protons they have. All right, there is some variance between atoms though. If an atom, or if one atom has a different number of neutrons compared to another atom, these two things are known as isotopes. So by technical definition, again, just rewording what I just said, atoms of different masses are going to depend on the number of neutrons they have. So if the proton defines the atom, if one atom has a greater number of neutrons, it's going to have a greater mass compared to a different atom which has lesser neutrons and it'll have a lesser mass. So greater number of neutrons, we're going to have a greater mass. The lesser the number of neutrons, the lesser the mass. And again, so we do see some slightly different physical or chemical properties, just subtly different depending on how many neutrons we have, but it is going to be the same atom, just different masses. All right, second, we also have the existence of ions. What happens when you increase or decrease the number of electrons that are present inside of an atom? You're going to get different ions. So here we actually do see a greater variance in terms of the chemical and or physical properties of an atom based off of how many electrons it has, but the variance, again, ends up being pretty consistent. Like if a lithium atom loses 1 electron, it behaves the same way as another lithium atom that loses an electron. And so we're, again, just defining an element by the number of protons it has, and the variance between the atoms with their elemental labels we call isotopes and we call ions. All right, so let's talk about isotopes first. So there are a couple of different ways that we notate what type of isotope we are working with. So in order to really lay out that notation, we have to define a couple of things. First is the mass number, which is represented by the variable capital A. The mass number is equal to the sum of the protons and neutrons that a particular atom has. So if we take the number of protons, which again is equal to that atomic number on the periodic table, add that to the number of neutrons, this gives us something known as the mass number. This is going to be important again for a moment, so just put a pin in it. The atomic number we are defining not only because we've already technically defined this, but we are defining it in terms of its symbolic notation, capital Z. Capital Z is always equal to the number of protons. So this is the number that we can find on the periodic table. In the square, wherever the element is that we're looking at. All right, so the notation we use to describe different isotopes then follows this notation, where X is the, elemental symbol. All right, so our elemental symbol is going to be kind of in the base. Our superscript, our A up here, is going to be our atomic or mass number, and the Z in the subscript to the left is going to be equal to our atomic number. So we have the sum, actually let's do this, here, sum of the protons and neutrons in the superscript, and solely the number of protons present in the subscript. So if you take A minus Z, this is going to equal the number of neutrons your isotope has. So for a specific example, we can see if we are observing the element neon, Neon has the atomic number 10 on the periodic table, and one possible stable isotope of neon is known as neon 20. So another way to rewrite this symbolic notation, at least how we would pronounce it out loud, write this down here, is neon 20. So we might see this notation, or you might have heard this notation before, particularly since isotopes tend to get discussed around nuclear studies, like nuclear radiation, nuclear weapons, like uranium, what is it, 258. That would be an element, an atom of uranium that has a mass number of 258. All right, so we can break down, though, the symbol notation for a number of different possible isotopes, and for neon, this is actually the comprehensive list of all of the stable isotopes. So we could have additional neutrons, so we can have more, 23 or more, or not 23 or more. We could have 13 or more neutrons, or even 10 or fewer neutrons, but these tend to be an unstable balance in the nucleus of proton to neutron. So the atom actually ends up decaying through radiation and falls apart. So these are the three stable isotopes of neon. These all, for all intents and purposes, again, behave as neon does, as we have recorded physical and chemical properties of neon. Each of these three isotopes would exemplify those properties. All right, we can collect all of the mass numbers of these neons. Notice that the subscripts are not present in these symbols that are here. And the reason why is that if you have your element symbol, the subscript with the atomic number, subscript with atomic number, is redundant. So we tend to not include the subscript with the atomic number, just because if you know the symbol, you already, by definition, know the atomic number, since the two, again, are in one-to-one correlation, and your atomic number can just be found on the periodic table, assuming you know the element. So because the atomic number is going to be the same across the board, each neon atom, by definition, has 10 protons. We just fill in this protons column a 10 for each of the possible stable isotopes. The difference then comes into play, or the difference becomes noticeable, recordable, observable. That's the word I'm looking for. The difference becomes observable when we count or calculate how many neutrons we have. Because again, the mass number minus the atomic number is equal to the number of neutrons. So for the first isotope that has a mass number of 20, we take 20, subtract out 10. This tells us exactly that we have 10 neutrons. Take 21 minus 10, this gives us 11 neutrons. 22 minus 10, this gives us 12 electrons. All right, so each of the numbers of neutrons is different here. Each of the masses of the individual isotopes are going to be subtly different as a result. Each of them, though, are going to characteristically behave as we would expect neon to behave. Now, because the element here is charge neutral, let's see, where am I rating it? Charge neutral. What this means is that the number of protons, which is represented by this P with a superscript plus, this is a positively charged proton, must be equal to the number of electrons we have, where the electron, and I've used this notation already throughout part 1 and here in part 2, here now I'm explaining it. An electron represented by base E with a superscript of a negative charge is a negatively charged particle. And the relative charge, as we've also discussed, is exactly equal. So if your species is charge neutral, you have to have the same number of negative charges as you do positive charges. And since each of these isotopes has 10 protons, they must also each have 10 electrons. All right, well, how do those isotopic masses of each of the individual isotopes connect to the masses that are present on the periodic table? Right, if you look at the periodic table, any elemental symbol, let's say carbon, has its name up at the top. We have a carbon. It has a representation of what the atomic number of that element is, and then generally on the lower half we have a measurement for how many atomic mass units that element weighs. So like carbon on the periodic table has 12.011, for instance. Well, how does this mass connect to the isotopic masses for each of the individual isotopes? Well, the relationship is that all of the isotopic masses average together to give us the mass that is present on the periodic table. So we have to take the average of each of the isotopic masses to give us what the general representation of the average mass of a neon atom is going to be. So the atomic masses on the periodic table are averages dependent on the abundance of the known isotope. So for example, with neon, each of the, again, stable isotopes we have present here, the mass numbers are present here. We can see that the mass number is approximately equal to the measured isotopic mass in atomic mass units for each of these isotopes. However, we are not just going to take a straight average of this number to give us what the average like atomic mass is for neon. No, we need to take into account how much of each of the isotopes are there in the universe. So if you've ever wondered why the periodic table changes, like why did the masses change? What's happening here? The reason why is as we continue to observe the universe and find the relative abundance, let's say if a particular isotope is greater or lesser than the other isotopes, we have to adjust our average over time. So the reason why we have to keep adjusting the periodic table is because we keep discovering new stuff as it exists in the universe. All right, so we have found though that neon 20 comprises approximately 90.48% of all of the observed neon in the universe. This means that we have to give more weight to its isotopic mass, the 19.992 atomic mass units, when averaging all of these isotopes. Neon 21 of the 3 stable isotopes we see actually has the least percent abundance of all of them, meaning that it is more than likely either the least stable of all of the stable isotopes, or just coincidentally it doesn't exist as much. The other two just happen to as in, I believe I'm using this term correctly. In physics it's known as asymmetric creation, where it's just because we don't know why yet, the existence of one piece of matter is for some reason more favored than another. So whatever the reason is, we have less of the neon 21. There's only 0.27% of it, of all of the neon we have observed in the universe, and the neon 22 we can see is 9.25% of all of the neon that we have observed in the universe. All right, so we need to take not just an average of all of these isotopic masses, but I was gonna box this, we need to take what is known as a weighted average. So again, the neon 20 comprises basically 91%, 90.5% of all of the neon that we know of, which means it needs to contribute more. It has more weight in the average than the other two. So how do we take a weighted average? Well, this is the equation that we can use to take or calculate a weighted average. In this case, we are going to be taking an average atomic mass. In order to take the average atomic mass, what we need to do is sum or add up all of the isotopic masses multiplied by, so that's what this means, it is multiplication. For anyone who possibly either hasn't seen dot notation or you rarely see dot notation, it does represent multiplication, and you will multiply the atomic mass by the corresponding fractional abundance of that isotope. Fractional abundance meaning, actually I'm going to write it up here because I'm going to need this lower space, not percentage. So you're going to take your percent and divide it by 100 in order to get the fractional abundance. This is a way to make sure that statistically your math is working out. You're not going to end up with atomic masses that are 100 times greater than what we would expect. We need to make sure again that we're taking that percentage, this is a percentage symbol, and dividing it by 100 to give us that fractional abundance to use in this equation. All right, so let's run through an example calculation. Here, we're just going to be using and I'm going to clean this real quick. We're going to be using our stable neon isotopes as our example. We can see again there are 3 different isotopes that we are going to have to sum the weighted average of all of their individual isotopic masses. So our first is neon 20, again with its isotopic mass of 19.992 atomic mass units. So there are going to be 3 different isotopic pieces of information we're going to have to sum here. So the first is that isotopic mass of our neon 20, which was 19.992 atomic mass units, right? What's a number without a unit? If you have a unit, you should include it. We're going to multiply this by the fractional abundance of the neon 20 isotope. The fraction, or the percent abundance we can see here is 90.48, which means the fractional abundance, when we divide this percentage by 100, is going to be 0.9048. So again, we want to make sure we're working in decimal form when calculating our average atomic mass. So we're going to write that right here, 0.9048. And all of this then corresponds to neon 20. We're going to add this, right? We're summing, so we're going to add this first piece of information to the weighted isotopic mass of neon 21. So neon 21 has an isotopic mass of 20.994. The percent abundance is 0.27, which means the fractional abundance we have to divide by 100, giving us 0.0027. All right, so in our equation then, 20.994 atomic mass units, and we're multiplying that by 0.0027. Notice that there are no units on the fractional abundances. And the reason why, again, is this is like a percentage. Like each of the pieces of this fractional abundance should sum to 1, meaning we are taking statistically literally everything that we can into account. It itself does not carry a unit, it is just a scalar. All right, all of this then pertains to neon 21. Last but not least, we need to sum the weighted mass of our neon 22. So we can see again, isotopic mass here, approximately equal to 22. It is 21.991. The percent abundance is 9.25, meaning that the fractional abundance will be 0.0925. So we've just, again, divided by 100. All right, 21.991 atomic mass units. Multiply that by the fractional abundance, 0.0925. And again, just to make sure I'm being explicitly clear, this is neon 22. All right, so we have all of the weighted isotopic masses now taken into account. We just have to add these things together. In crunching the numbers, again, bearing in mind that our unit in the end is going to be atomic mass units, our average atomic mass for neon is 20.18 AMU. Well, if we look at a periodic table, at least an up-to-date periodic table, we will find that in the square where neon is, will be an average of 20.18, and the unit of AMU is not going to be present, but there will be the number, which represents the mass, 20.18. So this is exactly where that average atomic mass is coming from. All right, so here we have breakout example problem time. So let's put to test what it is we have learned up until this point. This is the type of example problem that I would again encourage you to pause the video, see if you can't solve it for yourself. Spoiler, this problem does have a little bit of a trick to it, so as you are attempting it, keep in mind that it may seem like you are missing a necessary piece of information, but you can actually find it. So be thinking a little bit outside of the box, think creatively. Silver has 2 known stable isotopes, silver 107 and silver 109. If the average atomic mass that you can find on the periodic table for silver is 107.9 atomic mass units, And silver 107 has an isotopic mass of 106.9 atomic mass units with a natural abundance of 51.89%. What's your isotopic mass of silver 109? All right, so again, take a brief moment, take a pause in the video, break out the calculator, see if you can't solve this problem for yourself. All right, unpausing the video, then welcome back. I always say this assuming that everyone pauses, and I hope that you do, right? Science is, particularly learning science, is an interactive process. You can't just sit here and absorb everything I'm saying and hope to be able to, like, do this type of problem for yourself. So again, emphasizing, if you haven't already, please try this problem yourself. If you did, like, great job. Let's see what the answer is. All right, so let's gather everything that we know. Again, there's no shame in just gathering the information first. You have to know what you're working with. So we know that silver has 2 known stable isotopes. There are only 2 of them, silver 107, silver 109. So we know also on the periodic table that silver has an average mass of 107.9 atomic mass units. So what this tells us, just to go backwards and observe our equation, in fact, I'll just clean this slide off. We know what silver's average atomic mass is. We've been told that this is 107.9 AMU. So it looks like we're actually going to be finding one of the fractional pieces of information, and as we continue to read, that is exactly what we are asked to find. We are looking for the isotopic mass of silver 109. All right, so let's continue gathering things that we know though. So we are told that silver 107 has an isotopic mass of 106.9 AMU, and it has a percent abundance of 51.89%. Silver 109 is our big old question mark in terms of mass, question mark AMU. Right, in math they teach you like always use variable X, or that's the variable that's used the most commonly. I just honestly love throwing in question marks. I want to make it explicitly clear what are we looking for. So this question mark is going to represent our unknown variable. This is what we're trying to find. Well, in order to solve the problem, we need an additional percent. Right, according to our equation, if we are given an isotopic mass, we also need to know how much of that is there in the world in order to figure out what the average is. So it would appear as though we actually have 2 unknowns in this problem. But again, I did say there was a little bit of a twist. So we are told in the wording of the problem that there are 2 known stable isotopes. Again, 107 and 109, and that's it. Which means if silver 107 is 51.89% of all of the known silver, silver 109 has to be 100% minus how much we know of silver 107 exists. So 100 minus 51.89%. Right, again, 2 stable known isotopes. Between the 2 of the known isotopes, the total abundance has to sum to 100% because that's all there is. So if it appears as though we are missing a percentage, but we also know how many known stable isotopes there are, we can make a little bit of an assumption, and this is a totally valid assumption to make. So it turns out that the total percentage of the silver 109 ends up being equal to 48.11%. And so here now we have every piece of information we need to actually set up and solve the problem. We know, quote unquote, what the answer is, we know what the average is, and we now know what the, what both of the percent abundances are. We're given one of the isotopic masses. All we need to do is insert all of our information to our previous equation and solve for the question mark. All right, so let's go backwards and actually do that. We have 2 isotopes. The first we know has the isotopic mass of 106.9 AMU. And that particular isotope comprises 51.89% or in fractional form, 0.5189. All right, so this is near, or like just over half of all of the silver that exists, and the particular isotope that this represents is our silver 107. All right, we're gonna add this to our question mark in atomic mass units. Again, this is what we're looking for, so why not just make it explicitly clear this is a question mark, and the fractional abundance of the isotope that we don't know its mass, again, is 48.11%, which is equal to 0.4811. This component of the total sum of that weighted average, again, represents silver 109. All right, so algebraically, all we need to do is rearrange and solve for our question mark. So in order to do this, first, we're going to combine pieces, subtract it to the other side. So honestly, what I'm just gonna do is represent that we are going to take our 106.9 AMU times the 51.89%. We're just gonna subtract this whole piece, 106.9 AMU times 0.5189 to the other side. So we're just gonna subtract this to the other side. And then we have to divide each side by the fraction that is presented here, the 0.4811. Divide on the left-hand side by 0.4811. All right, so yeah, I'm making kind of like hand-wavy math here, but we subtract the silver 107 to the other side first, and then we divide by our fractional abundance. When we do so, what we're gonna find is our question mark is actually equal to 109.0 atomic mass units. All right, so we know now what the isotopic mass of our silver 107 is and the isotopic mass of our silver 109. Coincidentally, here we can see 109.0, where again, the mass number is approximately equal to what the actual isotopic mass is. So it makes sense. That's actually a really good way to be able to check your work. Make sure that your mass number is approximately, if not actually equal, to your isotopic mass. If it's not, there are a couple of places where the algebra could have gone wrong, right? If you're not following algebraic order of operations, your answer is going to end up off. Or if you don't actually convert your percent abundances into fractional abundances, again, your answer is going to end up being off, possibly even by up to a magnitude of like 100. So double check your algebra, make sure you're inserting fractional abundances, and if your math came out correctly, you should have an answer of 109.0 atomic mass units. So we've talked about isotopes now. The slight variance in the number of neutrons is going to give your individual isotopes different masses, and it is the average combination, the weighted average of all of those isotopes that gives us the average atomic mass on the periodic table. Well, there's another subatomic particle inside of your atom that can vary, and that is the electron. So as we vary electrons, we're going to end up with a different number of ions relative to, right, the atom, the base neutral atom that we're starting with. So if you are working with an atom that is missing electrons, this is going to be an ion that has a positive charge, right? If you're missing the negative charge, you have to have a positive ion. Conversely, if you are working with an atom that has extra electrons, the ion is going to have a negative charge, right? If you have extra negativity, your atom is going to also be negative. Now, since the relative charges are all whole numbered integers, we can very easily in our own mind kind of add and subtract how many electrons there are relative to the neutral species. That'll give us an idea of the charge. Formally, we can also mathematically define the charge as being something like an equation that we can calculate. If we know the number of protons in an atom and subtract out how many electrons are present, this will give us the total ionic charge. So for instance, in the table below, we can exactly calculate that based off of how many, what atom we are working with. We know how many protons there are, again, because this is a 1-to-1 correlation. Number of protons defines the atom, so if you're working, for instance, with something that has 8 protons, it has to be oxygen, just by definition. So we can pick out how many protons each of these elements has just by looking at the periodic table. And let's say we are, again, not working with something that is charge neutral. Let's say each of these potential atoms/ions has 10 electrons. Well, in order to calculate the ionic charge, all we need to do is look at the discrepancy of the number of protons versus number of electrons. In a neutral oxygen atom, we have 8 protons, and in theory we should have 8 electrons, but in this actual example we can see that we have 10. Well, the ionic charge then, we can see that there are 2 more electrons than what there should be based off of how many protons we have. Therefore, the ionic charge has to be equal to -2. Negative because we have too many electrons, -2 because exactly we have too many electrons. If we, again, want to use the equation we have defined up above, number of protons is 8, we're subtracting out the number of electrons, which is 10. This exactly gives us what we were able to reason through, -2 ionic charge. We can do the same thing with the other 2 examples, taking number of protons, subtracting out numbers of electrons. Neon, we can see, has no ionic charge. It is still a neutral atom. Sodium is missing 1 electron, right? There's 1 additional proton compared to how many electrons there are. This gives us a sodium atom that only has 10 electrons, a +1 charge. It is a +1 ion. There is a term that I want to introduce as we are working our way through this example, seeing now that the ionic charges can vary depending on how many electrons we are working with. This term is what we can see over here, isoelectronic. The atoms as they are presented in this example are in an isoelectronic series. What isoelectronic means, if we break down the word, iso means same, electronic means pertains to the electron. Right? Electronic, adjective of the electron, means it has something to do with electrons. So like, for instance, an electronic device like your computer or your phone is electronic because its function depends on the movement of electrons inside of the device. So the isoelectronic term that we can see here means that we are looking at something or a number of things that have the same number of electrons. Same, right, pertains to the electron, same number of electron. All right, so we can break down this word to understand what it means. And we can also then connect it to the example that we have looked at here. Each of these atoms and or ions has the exact same number of electrons. They all have 10 electrons. And similar to John Dalton's atomic theory, we can't have like half of an atom, we can't have 3/4 of an atom, we can't have fractions of atoms. Same thing here. We can't have fractions of some atomic particles. So we have to have whole numbered integers of the protons, the electrons, and the neutrons, and this will always give us a whole numbered ionic charge as well. All right, and that brings us to the end of our lecture on the distinction, the definitions, working with isotopes and ions. Here we can see a couple of section review problems. Again, I did go through and make sure that all of the page numbers align now with the 4th edition. If I happen to have missed a page number as we continue throughout this lecture series, please let me know in the comment section below. I want to make sure that I am actually updating my slides, making sure that they are accurate. The problems that I would suggest then, the first round all pertain to atomic number, mass number, isotopes, just being able to pick out what your atomic number A is, atomic number Z, mass number A, and the isotopic symbol. And then of course down below we have some problems calculating average atomic masses, again, just a couple of them here. All right, but yeah, that brings us to the end of our lecture. There's only one more part in the Chapter 2 section of this lecture series where we are going to then be paying more attention to atoms on the whole, how we can count atoms based off of masses, which is a really powerful tool to be able to really figure out how much stuff we have just based off of what it weighs. So yeah, that's going to be the next part. Hope you're looking forward to it. But in the meantime, if you have homework, do your homework, and class is dismissed.